A lot of houseware discussion in the next hour and a half. So looking forward to it. First group here, Jordan, Juliana, go ahead and take it away.
All right, good morning. I'm Jordan, and this is Juliana. We're going to be walking you through our design process for the Pathos air purification system. So to start, this was a collaborative project between MSOE and the Milwaukee Institute of Art and Design, MIAD. Juliana here is a product design student, and this semester she took a class where the focus was on a entry to the International Housewares Design Competition. I worked alongside her to accomplish this for my senior design project. The Housewares Design Competition is where the goal is to design a housewares item which solves a specific problem in the home. The submissions to this competition are judged on their design, research, and presentation organization. The problem that we decided to tackle was that of indoor air purification. According to the EPA, the quality of indoor residential air is often much worse than that of outdoor and commercial spaces. Poor air quality can lead to illnesses and other long-term health issues. Since people spend much of their time in indoor spaces, having quality air is important. This poor air quality can be caused by poor ventilation, volatile organic compounds or VOCs, and humidity, among other things.
So after establishing our problem statement, we looked at the current products on the market, both dehumidifiers and air purifiers, and realized there wasn't really a system or product that reached the whole home yet was also compact.
And most of these products only attempt to address one aspect of the problem. These aspects being air purifying, dehumidification, and ventilation. I conducted background research on various methods to solve this problem, with these being my main focuses. For air purifying, we have different air filters, ionization, and UVC light. For dehumidification, I looked at various types of dehumidifiers, such as the classic vapor compression dehumidifier, thermoelectric dehumidifier, rotary desiccant wheel dehumidifier, and also just using like solid desiccants as a method of dehumidification. For ventilation, it's mostly different types of fans, such as exhaust fans, as well as other easily available types of fans. I don't have time to dive into all the details of my research, but if you're curious, you can ask about it at the end. So now I'm going to introduce our solution to the problem, the Pathos air purifying system, which consists of two main systems. We have the air purifying module, which is battery powered and wall mounted, and then the battery charging hub for recharging those batteries, and this is also wall mounted. To achieve whole home air treatment, you would use multiple air purifying modules and one hub. The engineering focus of this project was on the air purifying module. So now I'm going to define kind of the subsystems of this project. We have the air motion, where the air moves through the product and from the room through the product and back into the room. Dirty air in, clean air out. The air treatment section removes contaminants from the air, while the dehumidification section maintains the desired humidity levels in the room. The instrumentation section senses air quality, temperature, and humidity levels, while the communication and control section controls the fan and any other components that need to be controlled, as well as provide information to the user. The power subsystem provides the required power to all electronic components. Now some objectives and constraints. Kind of the overall product objectives and constraints. We're trying to aim for the product to be less than $1,000 and use multiple modules to purify air throughout the whole home. The product should meet the purifying, ventilation, and humidity requirements of the space with minimal user interaction. Some constraints here, we have a single module of the product should not be larger than 800 cubic inches and should be made using eco-friendly and sustainable materials and manufacturing processes, as well as having minimal environmental impact at the end of its life cycle. Some subsystem objectives and constraints. For the air motion subsystem, we're trying to achieve at least 2 equivalent air changes per hour in an average room and operate with minimal noise. Some constraints are a constraint here is that the product must have variable speed airflow. For the air treatment subsystem, we're trying to remove 99.95% of contaminants from the air and only have the filters need to be changed about once every 6 months. The product should or must filter particulates, bacteria, VOCs, CO2, odors, and humidity. And for the dehumidification subsystem, we should be trying to achieve a relative humidity of less than 60% at normal room temperatures. And in this case, if the desiccant is used, we need to shield the desiccant when the humidity is too high. In the subsystem, or for more subsystems, we have the power subsystem, where if the product is battery powered, we should be trying to only need to have the battery be recharged at once every 3 days. And all electronics must be moisture resistant. For the instrumentation, we should be attempting to monitor air quality, humidity, temperature, and airflow rate. And for the communication and controls area, we should be trying to adapt to current air conditions while communicating information about each module to the user, as well as providing helpful tips and information on improving air quality. Next, we have the design formulations, where components that would aid in solving the problem were selected and weighted against each other. These parts selected would help inform the overall look and design of the product, and for the air motion subsystem, several different types of fans were compared. Ultimately, this 12-volt DC axial fan with a circular frame scored the highest. For the air treatment design formulations, several different types of air filtering methods were investigated, with each different type of filter being intended to capture a different size or type of contaminant. Ultimately, this special Lanico Ecostatic, naturally sourced from wool, sheep's wool material, was selected to be used in conjunction with activated carbon filtering for a wide range of contaminants filtered. For the dehumidification subsystem, we had kind of decided to use the desiccant method due to its simplicity among other factors. And with these desiccants meant that a solution for sealing the desiccant was necessary. So these are some of the things that we compared. And ultimately, silica gel was selected for dehumidification, while 13X molecular sieve was also then selected for a CO2 version of this section. For the sealing method, a double iris mechanism scored the highest, so that's what we want. For the instrumentation, many different sensors for all different kinds of sense capabilities were compared. And luckily, there was a sensor which achieved everything that we needed. The materials and manufacturing were was a topic of much debate throughout the duration of the design. And aluminum was the first material that was kind of considered and explored throughout the design process. In this case, die casting would be required to achieve the unique shapes. And to get the color and finishing, it would be ceramic coated and anodized in certain situations. There's a lot of issues here with weight and cost, especially since this would be a wall mounted and there's complex shapes and stuff like that. So an eco-friendly polymer such as PLA was suggested as an alternative here, where it would be injection molded, and to get the kind of color and shape or color and finishes, physical vapor deposition would be used. Going forward, I will be considering this PLA solution.
So my portion was to take all of this engineering and make it fit seamlessly into the pump. And so we went with the ethos of it being clean, lush, and soft to fit a very foamy aesthetic. Heading into ideation, I got a lot of inspiration from wall-mounted light sconces, and we ended up with this cylindrical, wall-mounted, potentially modular, potentially adjustable design. The reason for this cylindrical form is because form follows function, and cylindrical shaped filters are the most effective at capturing those pollutants that we talked about. We also needed to design the charging system. This was a very simple design, just basically a box with a digital display to fit seamlessly into a main environment in the home, such as Going into mockups and user insights, I created what we call alpha prototypes, which is basically just low resolution hardware mockups to get a user's feedback. And I walked away with the things that the user values and doesn't value. They value the modularity of the system as well as it being wall mounted. And they didn't necessarily need the adjustability factors. They wanted to set it up and just enjoy it. We also did user testing on the charging system, and we had originally considered it being tabletop. They didn't really value that. They also wanted it to be wall mounted. They really valued the simple design as well as the potential for a screen display. So all of this led into our final design direction. The reason for the name, the Pothos, is because the Pothos plant is a naturally air purifying vine plant, and we named our systems off of those parts. The stem is the base filter that has that wool and activated carbon. For main air purification, the node is the system that contains those two iris mechanisms, and we house the desiccant canisters. Root is the humidity capturing desiccant, and leaf would be that CO2 capturing desiccant. And the battery charging system is named Sol after the sun that charges the plant.
So now I'm going to move into kind of our current design CAD. And here we can see kind of how the basic stem model can be used with the node addition to result in the combined kind of module for additional air purifying. Dissecting the combined module into smaller parts, we can see the electronics housing and wall mounting there, the air motion section at the bottom, the stem housing and node bypass in the middle there with the air filtering section here. And then on top of that, we have the node addition. So kind of diving into some of those areas further, we have the electronics housing and wall mounting. Here we can see the wall mount here. Gets wall mounted to the wall, and then the electronics housing slots into that. The electronics housing here, we can see the microcontroller, which rests there, and this controls the whole system. The gas sensor has venting at the bottom there so that it can easily get the air from the room. And then the battery slot here goes through and powers everything. And the battery slides in there. And so you can easily remove the battery slot here, and take the battery in and out. As far as the main stem housing and air motion, we can see the fan housing and the fan at the bottom, and these connect to the main housing. This main housing has a slot for the filter, and the filter can be easily then removed, or the slot can be removed and the filter removed for easy replacement. Up here we have the node bypass valve, which I'll get into further detail later, and it is actuated via these latching solenoids here. As far as the node and iris valves, the node is kind of set up similarly to the kind of main stem section. We have the main housing with the slot for the desiccant and this canister which goes in that. So you pull out the desiccant slot, remove the canister when it needs to be replaced. Kind of sandwich this canister, then sandwiched between those two valves. These valves can open and close depending on whether or not the canister needs to be sealed or not, depending on the current conditions. And they're operated via those servo motors over there. This is all kind of sealed together with this back housing to keep it all together. And the air inlet cover goes on top of that. Kind of diving into how the irises work, we have the two covers, the servo side cover, which holds the servo and holds everything together. And then the base cover, which kind of lines everything up. This driving here connects to the servo and this intermediate gear. And this intermediate gear goes to the two leaf gears, which have an interlocking pattern to help with sealing. Those last two sections I went over kind of outline the desiccant sealing system. So here we have some cross-sectional views of our product in the various configurations and the airflow that can be found in each. So the basic stem model, the fan is pulling the air through the filter and out, and that's all that is happening there. When you need additional filtering, such as CO2 or humidity, you add the node on top. And the fan then pulls the air through the node, through the desiccant, and then through the filter and out the bottom. Here you can see that the irises are open to allow this to happen. The bypass is closed so that the air can only go through the whole system. In a situation where the desiccant would need to be sealed off, for instance, if the humidity was too high and the desiccant would get oversaturated, or not oversaturated, but too saturated and become useless, the iris would be closed on either side, sealing it off, and the desiccant bypass valve will be open, allowing the air to go through the filter and out the bottom as usual. Some analysis I conducted on this product were the air purifying capabilities and battery life estimations. The air purifying capability calculations are very similar to that of ventilation and HVAC, which uses air changes per hour, which is like how much air is being refreshed in the room in 1 hour, or changed in 1 hour. It's very similar for air purifying, except it's called equivalent air changes per hour. Since you're not bringing new air into the room, you're simply purifying the air and refreshing it. That is calculated identically in both scenarios. And so you have the volumetric flow rate of the fan converted into hours divided by the room volume. And using the flow rate of the fan we selected, this results in a maximum amount of air to be changed in 1 hour of 4,242 cubic feet. In an average room, this equates to about 5 equivalent air changes per hour as the maximum that can be achieved. For the battery life estimations, we kind of made some assumptions here that our battery was equivalent to the amount of batteries that would fit into our current battery, the amount of AA batteries that would fit to our current battery footprint, and in a certain combination of series and parallel. So to get the required voltage needed, you simply put the batteries in series, and it took 8 AA batteries to reach the required voltage. Using 2 of these setups in parallel would get a battery capacity of 4.6 amp hours. And using this equation here, by estimating our load to be at the maximum fan power, it's just assuming that the fan isn't running at max speed all the time. The average fan speed, the battery life was estimated to be about 50 hours. This is a little low, so to increase this, the battery footprint would need to be increased. So the current product specifications, the overall air purifying module, like the combined module, has dimensions of 13 by 6 by 8 inches, roughly. The stem module itself is 10 by 6 by 8, about, and the node add-on is about 3 inches by 6 inches by 7 inches. And this module can filter dirt, dust, pollen, bacteria, viruses, odors, VOCs, and depending on the scenario, CO2 or humidity. The maximum airflow of this is 70.7 CFM, and it operates using a rechargeable 12-volt battery.
And so how do we take this and make it marketable for the public? We do this via color, material, and finish. We have 2 main aesthetics, a dark aesthetic and a light aesthetic, with then color touch points where the air flows through and where it is mounted to the wall. I was the one advocating for it to be made out of aluminum because it is a lot easier to market aluminum as sustainable rather than that eco-friendly plastic.
So my plan for next semester, I need to start with model refinement, focusing on functionality, usability, and manufacturability. Throughout that, I'm going to try to keep kind of the main look and aesthetic of the exterior of the current design. But if changes need to be made that enhance the functionality, usability, or manufacturability, I will be making those changes. I will also need to be sourcing the parts that will be used for the prototyping, and these might vary from the parts that I have sourced thus far. From there, I will assemble the prototype. Well, I guess before that, I will purchase the parts and 3D print, the housings. Here we have kind of a rough mock-up of like a non-functional prototype. And once the prototype is assembled, I will work on making everything functional, as far as monitoring the air quality and adjusting the airflow based on that, as well as sealing off the desiccant section when required. And I'll be doing this using a microcontroller and sensors. Based on testing that occurs throughout that process, I will then refine the prototype. And once the prototype has been refined to its final model, it will be finished with the proper coloring and finishing and all that. Currently, I'm estimating that I will have this done by May 8th of next year. Thank you all for listening. I would like to give a special thanks to Dr. Hart for advising me and helping out with this project. Any questions?
Thank you.
I can't remember if this was a constraint or a criteria.
Yep.
You wanted to be able to move 99.95 of the contaminants.
Yeah.
Is that of the room or of the air that the unit sees?
Is there a difference in that case? Like,
Well, that's my next question. Well, no, I'm just like, right now, I'm just like, but that was,
it's probably with the intent of the air going through.
well, no, but that was in your problem statement and your criterion constraint. So for this design, is this design, what was your intention?
To remove contaminants from the air.
Again, of the air that comes into the unit or of the air in the
Well,
room?
it's purifying the air going from the room into the unit, right? It's being circulated.
My next, okay,
Yes.
was this like, is this for a room that has like a forced air system? Or is this, or like, tell me about your assumption. And again, I'm only interested in like what your assumptions are.
Yeah.
Because if you have a radiator situation or you have passive heat, your airflow is going to be different than if you have a forced air system.
I mean,
Did that come into your consideration?
not entirely. We
Okay.
were assuming that the fan is gonna pull air through and circulate itself. Obviously, homes have their own
Yeah.
air ventilation system, and it wasn't entirely considered.
So you didn't really look into like how the airflow in the room would work and
Well,
how
how it would affect the system?
Yeah.
No,
Okay.
and it probably should.
Okay, and I would have the same kind of question in terms of winter, like summer versus winter.
Right.
Okay, okay. Oh, no, I'm just like trying to
Yeah.
get an idea of,
For sure.
of that. I'm a big problem statement person. I really want to understand the problem. Okay, I'll let some other questions.
Many questions?
Yeah. Very good work, Jordan. Just want to ask you about the name adaptive when you say adaptive.
Yes.
Do you have like any adaptive feature? Like, for example, when you start working about in the mechatronics part, the controller, will you have like an adaptive controller to adapt to the environmental changes? Like, what's the meaning behind adaptive here?
So the way I'm kind of looking at it is the system will adapt to the conditions, as in if it needs to move the air quicker to filter more, it will use the sensor to be like, oh, we're below a certain threshold, and the fan will work harder.
Okay. Okay, yeah, just make sure to make this more clear, because let's say if you're thinking about publishing this, control people will get after you, because when you talk about adaptive, there are so many things in adaptive, especially the control theory.
Right.
The second question you mentioned, you talked about the battery life, and you said the battery life was low when you did your analysis, right? Did you try to investigate the problem behind it, or this is something that you will do?
It's something that I'll look into next semester. I was kind of crunched for time at the end there.
Okay, okay. So very good work. Congratulations.
Thank you.
Okay, I have another one.
Yeah.
What's the overall weight? And when you mount it on the wall, you have to have the studs. You have to go into the studs. Or
This is something that I didn't address yet because I had to cover everything, but it's definitely in my mind.
No, like, yeah. I have an old house, so some of this is coming from. Yeah, and we put in our own forced air system, so like the whole airflow thing is.
Yeah.
But nice project.
Other committee questions? If not, maybe we got one from the general audience, if there's any general audience questions.
Yes, there was some, we were looking into like, when you need to change out the desiccant, you can send it back to the manufacturer basically. To have them recharge it, which was something that I guess I didn't really talk about, but the desiccant can be recharged. Like you just have to heat it back up. We're just gonna have you send that to the manufacturer.
I was curious also on that line of reasoning, if the humidity in the room is higher than what the desiccant is capable of handling,
Yeah.
would you receive a message like add another node, or do you require more desiccant, or would it just kind of automatically close the iris and say like open a window or something like that?
That's exactly what it would do. And if it was in a bathroom, which is where this scenario would be seen, we'd say, make sure your fan is running, open a door, open a window. Obviously, there's some caveats there that you're hoping that it does what it needs to, but yeah. Oh, yeah, there's an app. This is kind of the display on the hub. And then an app that does all that too. This is all new on this work.
That's awesome. Okay, one special thank you to Juliana for being here. It's not, her requirement to be here for part of this, so thank you for coming. And one more special shout out to Professor Frank Savage, who was on the Maya side advising us as well. So let's thank these two and we'll move on. What was it?
That's my roommate.
Yeah, it's cool. Yeah, you did an awesome job, and even having the model, maybe we could have.
Oh, yeah. Well, it's a little fragile.
Because it's PLA.
No. Because the parts aren't actually together.
Yeah, very cool. You guys clearly worked very hard, so thank you. Okay, so got a couple minutes for changeover. We're gonna start right at 11. So you guys got a couple, I guess, but Aiden, you got a couple minutes here to before we start. We'll try to stick right to the schedule.
Sorry, I'm sure that.
Yeah, like how much a bump would you out does their unit pick it up with like normal filtration and maybe that's happening is another concern. Yeah, it's hard to say, right? What is the air in the room relative to the air in the module?
And
Maybe.
and how much module, and how much module, so
Right.
yeah, you're never gonna get the air together, like, you're gonna have stagnant.
Right. You don't want that near so much of what you're actually doing.
One of our air returns, high or low,
Yeah, sure.
depending on whether you want to maximize.
Air in, for the HVAC, things like that, yeah. For sure.
I've seen the locations of, we had to change one of our air returns and the airflow in the house.
Yeah.
Like the airflow, yeah.
So you get like cold spots. Or
Oh, that's an awesome.
Yeah. It's, yeah.
Definition, yes.
Maybe it could be marketed for homes that don't have central ventilation.
Yes.
Just 1 second. Sure.
This one hits real close to home.
That's the idea. It goes really as possible.
I'm good for it.
Yeah. Thank you for staying on Friday to do some of the evaluations. Appreciate it. See a little bit of the senior design too.
Yep.
Understand it.
Like over this is not my area. My area is more in control. Like I just do like.
Yeah. It's
Yeah.
more like everyone get a little exposure to design and I know, That's just kind of just a general design kind of thing, I think. So it's good to just see it. Okay, 10:59 and 30 seconds. So we'll go ahead and start with the next talk. Aiden also participated in the housewares design competitions. We'll let him kind of start and take it.
Good morning, students and faculty. I'm Aiden Linder, and today I will be talking about my redesign of the whole room. So first off, I want to give you context on how this project originated. I'm sure you heard about it from in Juliana, but this project was created in collaboration with the Milwaukee Institute of Art and Design, and it is an entry into the International Housewares Association Design Competition, which is a competition that showcases the top student designers in designing houseware products. Myself and my Maya partner, Nick, got together and chose what category listed here, straight from the IHA website, that we wanted to tackle. And we ended up going with the outdoor products and maintenance category. We began the semester working together, but recently we have moved to work individually. So now I'm working by myself, but the same project goal still remains. So the problem statement I have here is the main causes of kinks, punctures, and leaks in hose systems are mainly due to the way the hose is stored. More specifically, the way it is wound can cause folds in the hose, which block the flow of water, along with poor installation and corrosion from the fittings, leaks to water waste and that's weaker flow from those attachments. Now I'm going to take you through some existing products. What we have here is one of the most common uses of a garden hose rail, and that is a plastic wall-mounted hand crank. It does its job in winding the hose, but the lack of mobility, the possibility of tangling due to the orientation of how the hose is wound horizontally as well, can cause kinks in the hose, and being open to the environment are the cons to this product. This product is much like the last one. It's a hand crank rewinding hose rail, which does its job, but it has the same problems with tangling and bunching due to the orientation of how it is wound without a guiding system that evenly distribute the hose, and it is also not mobile. However, this hose can be completely enclosed inside the box, protecting it from the outdoor elements, which is nice. But this can also be annoying in the box with some hard to reach places maintenance on the hose. This product looks most like what I was envisioning. This is a mobile hand crank hose reel with a guiding system and all-terrain wheels. While there is a guiding system, there is still risk of the hose tangling while rewinding. And this product also exposes the hose to the outdoor elements, which can cause damages. And a common problem with the last three products that I have also showed you is that they are not automatic retraction as well. This product, however, is an automatic retraction method that completely encloses the hose and retracts slowly and safely. But the only problem with it is that it's motor controlled and the fact that it's also not mobile. With this background research in mind, my final design goals were to have a mobile system that automatically retracts with no electronics involved in the mechanism, is lightweight for ease of maneuvering, long-lasting so the user can rely on it for a long time, and it also completely encloses the hose to protect it from the outdoor elements. Which brings me to my final CAD model of this project, with the hose reels attached to the image on the left and just the cart frame on the right. The key features that I want to highlight are the two hose reels. I have two because I want one that extends and retracts as the user walks away from the hose spigot, and one for the user to extend and retract with the hose that they want to grab and use. Frame pieces on the right are tubes that are connected via slip-on fittings, and the hose reels are attached to the blocks that are labeled on the right there with T-slots, which I will also get into in a bit. Which brings me to my subsystems here. I'm going to start off with the first and most important one of the three, the latching/retraction mechanism, which accounts for the control, extension, and retraction of the hose. It also provides a latching and locking mechanism for the user to lock the hose at a specific length. And also it provides the automatic retraction. I also have the cart, which accounts for the mobility and transportation of the system, the structural support and load bearing. And also it provides the stability during use. I also have the hose housing and casing, which accounts for the storage of the wound hose and also the protection the overall protection of the hose and inner mechanisms. My objectives for the cart subsystem are that it should be easily assembled, easy to remove the hose reel, while the non-negotiables included not being wider than 3 feet. It should be able to hold up to 30 pounds and should have ground feet for stability. And the material should be corrosion resistant and it must be. For my mechanism subsystem, my objectives were to have the ratchet mechanism be easily released by the user whenever they please, having the ratchet be a part of the housing, and for the motion of the winding to be smooth. The constraints were to have the retraction take less than 30 seconds because probably watched it was wound up. Have it last 10,000 cycles, which is about 5 years if used regularly. And that the mechanism should be purely mechanical, which means there's no electronics involved. For my housing and casing subsystem, my objectives were to have casing able to be opened for maintenance access, the casing exterior part of the system that attaches to the cart frame. And the housing should have a hole to feed the leader hose through. And for cleaning purposes, the case should have a brush outlining the opening for the hose to run through. And the constraints for the housing and casing is that it should hold up to 50 feet of hose length on each side, so that it's about 100 feet of room. And the maximum diameter of the hose that the housing should hold should be about 5/8 of an inch, with the standard being 1/2 an inch. And the thickness of the casing should be at least 5 millimeters to be able to withstand the outdoor elements without deformation. And the casing also must fully enclose the reel and mechanisms to ensure maximum protection. So my design concepts for the cart, I have the frame material, which I chose aluminum, stainless steel, and PVC, all for their corrosion resistance capabilities and their strength. I have the method of assembling the frame, which is threaded fittings, slip-on fittings, or strong adhesive. Continuing on with the cart design concepts, where I have the hose reel attachment method. I have 2 plates with the slide-on tracks, threaded pipe attachments, or just welding it. I have the wheel types, which I will use on the cart. I have caster wheels, wheelbarrow wheels, and standard rubber wheels. And I also had to take into account the wheel orientation, which I came up with the options of having 2 wheels on the back on a non-rotating axle, 4 wheels on a non-rotating axle, and 4 wheels on a rotating axle. So here are my pew matrices for the cart frame material and assembly method. And for the frame material, I consider density and strength the most, because I wanted the frame to be both lightweight and strong. And I ended up choosing for that. For the assembly method, I considered structural strength and ease of installation the most, because I wanted the frame to hold up well under outside loads and to be easy to be put together. And I ended up going with the slip-on fittings, which are going to be secured by set screws, which I will show you later. For the reel attachment method, I thought stability and serviceability were important, because the reel must be secure in the frame while it's moving around bumpy terrain. And it needs to be easy to remove from the frame to run maintenance on it. And then ended up going with the plates and side tracks. For the wheel type, I considered durability and load capacity the most, because with load capacity, the wheels have to be able to hold up the entire system, right? And for durability, it's got to be able to withstand rough terrain. And for the wheel orientation, I considered the ease of steering and ease of installation the most, because having a cart that's easy to maneuver is much less of a headache. And having a ease of installation just overall speeds up manufacturing process. The design concepts for the winding mechanism, I went with a clock spring, which you can see up here, and clock springs are the way that tape measures are wound up, if you've ever taken one of those apart. I also considered a clock spring and gearbox for this was an idea that Nick and I originally came up with to have a clock spring wind up the housing, and a gearbox system would be connected to a guiding system that would look back and forth as the clock spring wound. And I also considered the motor control option purely for comparison with these two purely mechanical options. So for the down selection of my retraction mechanism, I considered life cycle and reliability the most, because we needed to last a long time without needing maintenance and to be able to reliably run it every single time. And I ended up going with just the clock spring. So for my casing and housing concepts, I only considered the material, which I came up with polycarbonate and ABS plastic, both for their lightweight and costs. I considered stainless steel for strength, a hybrid between metal, steel, and plastic to have it be strong where it needs to be and lightweight when it needs to be. And I also considered aluminum for the proficient strength, lightweight and cost compared to other metal alternatives. And I also considered all of these options based on their corrosion resistance capabilities. For the materials for the housing and casing, I wanted to prioritize strength and lightweight properties, and I ended up choosing polycarbonate plastic for the housing due to its low density, and aluminum for the casing due to its proficient strength, ductility, and low density for strength purposes. So now I'm going to dive into my CAD model. What you see here is an isometric view of my highest level assembly with both hose reels attached, which you can get a closer look here with the T-slot shown on the support block with a little chamfer to give room for the insertion of the material. What you see here is an isometric view of the frame by itself with no hose reels attached. The frame is made up of aluminum tubing, which is connected with the slip-on fittings with set screws, which you can get a closer look at here to see how those are connected and set. You can also see the four support blocks that are plated to be welded onto tubes as well. The frame itself comes out to about like 3 feet wide, and it extends out about 2 feet. So getting a closer look at the wheelbarrow wheels, the shaft runs through the tubing across the bottom of the frame and into the ball bearing attachment on the wheel, and is also secured with those fittings and set screws. And the shaft running through the tubing is about 3/4 of an inch. Looking closer at the casing, you can see the opening right about here, and that is one gigantic rectangular opening because the hose is going to be exiting the hose reel from a different height as it extends out, and that just allows it to have a smooth exit with no awkwardness and risk of kicking. And the T-slot, which is on each side of the casing, helps with the attachment to the frame. You saw that in the first view. You can also get a closer look at the latch and the hinge, which go on the top and bottom of the casing. And those are connected with, or attached, I should say, with thread cutting screws, which are sizes 6 and 8 respectively. Now I'm going to dive into the housing and mechanism portion of the CAD model. The housing is planned to be made of polycarbonate plastic and with the injection molding and the ratchet teeth being a part of it as well, because the entire thing is rotating about this ball bearing right here, which is attached to the backside of the on the backside of the housing with the bearing shaft running into the casing portion cavity. And the clock spring that you see here is attached both to this notch right here, which extends out from the housing, and this notch right here, which is attached to the casing. This notch does not rotate to help the spring build up tension. And as you can see here, it's attached. There's a little slot opening that the clock spring can be inserted into. And this clock spring that I'm using has a life cycle of about 10,000 cycles, and with the max torque being about 0.1864 Newton meters and a torque of 0.0311 Newton meters if pre-wound 5 turns, and that would be at the end of the working. What you can also see up here is the ratchet pin. The ratchet pin is on the inside of the casing, and it extends out to the ratchet teeth. And one thing I'm going to do next semester is attach a torsion spring to this ratchet pin to ensure a more controlled to ensure I have more control of the ratchet pin. And this release notch right here can be just turned by the user to release it when they want to. And the housing diameter is about 25.125 inches, which is just this part right, this whole part right here, this whole plastic part. And I forgot to mention it before, but the casing diameter is about 32 inches. So now I'm going to be diving into the analysis that I ran. First, I had to get the mass properties of both the housing and the hose. So I assumed that the density of polycarbonate was about 1,200 kilograms per meter cubed, along with, and I got the volume of the housing from the mass properties in SolidWorks, which came out to about 0.0027 meters cubed. And for the hose, I assumed that it was full of water because I could wind it up while it's full of water while it's empty. And I calculated that by adding the two weights of the two components together. And I assumed the density of water was 1,000 kilograms per meters cubed, and the density of the rubber hose would be 1,100. For the rotation calculations, I used the mass moment of inertia, which is the property that measures the difficulty to change the rotational motion of an object. And the initial mass moment of inertia was when it's just the housing. I only considered the mass of the housing because this is when the force is like fully extended. It's completely out. And the radius stays constant because I'm assuming it's just the radius of the housing. And my initial and final moments of inertia were 0.6522 kilograms times meter squared, and about 1.61 kilograms meter squared. For finding the initial and final angular accelerations of the model, I used the relation torque equals I alpha. And the initial angular acceleration is when the clock spring is at its strongest in torque, and is used. I used the initial maximum from inertia, and for the second angular acceleration, I used the minimum torque and the maximum, or the final maximum inertia, I should say. So getting into my my model for how I can model the angular acceleration and angular velocity over time or over the angular displacement. I took the difference of the two angular accelerations over the 94.96 radians of displacement. And to get omega in terms of theta, I integrated the alpha equation based on theta, and the time in terms of theta is the integration of the reciprocal of omega sub theta from 0 to 94.6 radians. And here are my results from the model, and over integration in Desmus graphing calculator, I found that the host would take about 28.83 seconds to retract. My plans for MEC 4902 is to finalize the frame layout, figure out how the reels will connect, and to attach the brush onto the casing, along with attaching the torsion spring to the ratchet pin, which I talked about earlier. And for prototyping, I want to prioritize the mechanism. That's the most important part. And some additional analysis that I will run is stress analysis on the card frame to make sure it doesn't fail. Thank you very much. Special thanks to Dr. Hart and Professor Savage for advising me on this project. Have any questions?
Okay, thank you. Okay, about 5 minutes for questions. Committee members first.
But
Do you want to go? Okay.
there you go. Okay, I went first.
Okay, so I'm still a little bit confused about the problem statement. So is it about the latching and the mechanism itself of the hose? Or about the fluid moving in the hose? I mean, like why you were doing this just for the sake of the competition? Like you are redesigning the hose.
Yeah, so my problem statement mainly addresses the kink risks of the hose, which results in like permanent damage, and also and it was more the automatic retraction was more for user convenience as well. But I think the main thing I wanted to address was the storage of the hose improving as well, which I should have gone into depth for, but I was in one of my CAD views. I had the hose like stacked on top of itself, so there was no horizontal displacement when winding up the hose. Did that answer your question?
Okay, and you mentioned no electronics, so just the mechanism to be pure mechanical. Is there a reason behind this? Why it's pure mechanical? I mean, everything now is electrified. I'm with the electric.
Also to have less problems occur. Like if there was something wrong with the electronics as opposed to as opposed to the mechanism itself.
I mean, like nowadays, it's very rare to have problems with electronics. Nowadays, like if I want to buy your, let's say, this house, how can you convince me, like, not to get the electronic part and I have a pure mechanical part? I mean, do you think about adding any electronics or you don't want to add any electronics at all?
I don't think about that. So that it's the constant exposure to water that the mechanism would have. So if anything were to go wrong, I just drop the for electronics.
And I have a third question. You mentioned that you want to add a torsion spring. So can you just explain for me where you want to add it and why you want to add it? I think in one of your slides you mentioned that.
Yeah. Okay.
Yeah, because the clock spring it's a torsion.
Yes, I was planning on having the torsion spring to this ratchet measurement right here. I'm gonna dive into this more into next semester. That was something I planned on attacking next semester, but it's gonna be attached to this ratchet pin right here so that it can be more secure and follow the ratchet mechanism more closely.
Okay, is it something for safety or just for the mechanism to improve the mechanism?
It's to improve the smoothness of the mechanism.
Okay. Thank you so much.
Okay, maybe one or two.
I have a quick question, I think. So you said I'm trying to kind of imagine like how this is mobile. So is it mobile that this will be attached to the faucet and you wheel it in your yard? Or do you wheel this, like, so what's the mobile part?
So so what I envisioned for this this project, here we go. Yes. So this hose reel is meant to be for the user to extend and retract the hose that they actually use, and this is going to be attached to the water supply from outside your house so that you can walk away from it and walk towards it, and it's going to like extend and retract
So,
as you walk.
okay, so I have a hose, it's attached to my house.
Yes.
Am I walking with the hose or am I walking with the cart?
Walking with like once you attach the supply hose to the spigot, you can walk away with the cart.
So I'm pushing the cart and the cart is unreal,
This
Like twice the distance.
this reel is unwinding as you walk away from the water supply, and then once you get to where you want to, you can then move to this and use what you want to from. Yeah.
Would it be accurate to say that you can effectively maximize your hose length by 2 because you could either choose to leave it stationary and retract the hose, or if you need to like go around the corner of your house, you would wheel the cart and then you could retract the hose from where the cart is.
Yep, it would be completely up to you.
so where's the 50 feet? Is that 50 feet total or 50 feet per reel?
50 feet per reel, so 100 feet.
A lot of those. Okay, maybe one more question, quick, if you got a quick one.
Do you have the ability for it to be easy to drain?
Good question.
Apparently, no, that's fine. You might want to consider that because one does need to drain the hose prior to winter. Yeah. See, when you have a homeowner,
True.
I'm not even gonna ask about like the stiffness of the hose, you
Yeah.
know?
Okay, thank you, Aiden, we got a
Thank
little.
you. I don't think electronics would enhance this, but I'm old as dirt compared to my.
Yeah.
I'm always with electronics.
You always want electronics?
Yeah, for sure.
I'm like, yeah.
I can clearly see all of the perspectives that are happening now.
Yeah. You guys got the presentation for the way there, the little thingy up there? Yeah. All right. More housewares coming at you.
I know, I saw.
They're very different though, you know? I mean,
I like the
You're
different.
like the perfect person to be on this panel.
the homeowners, very different. Yeah, the
It's
homeowners.
like a competition.
Not only a homeowner.
Yeah, they submit to this.
She bought a house.
House
Okay, do they
competition.
get fund to
Oh, yeah,
build
that's,
their
Yeah,
prototype?
yeah.
Is it
So-
funded?
I mean, we fund them with the ME department money.
Okay.
Um, yeah, but, do you guys need a second?
No, we can,
Let's wait 60 seconds and then you guys can.
I'm good.
Or,
Yeah.
that's this long, like phone, telephones. Do we want to line up this side on the percent and then shoot out? And what do we want to line up across the board and whoever's presenting? All that, like, what do we want to throw to be, have a bigger resource, but I was. I where I was like, oh, I think we want five.
make sure to like speak like to the camera.
Yeah, thank you. We can just hand off the changes. Oh, okay. You're good. Yeah, we can just go down the line. That's better. So. Then you. Or no. Yeah. Yeah, let's just.
Okay, we can go ahead and get started. 11:31. Another housewares design competition entry. So let's hear all about it, guys. Go ahead.
So hey everyone, my name is Joseph Moore.
I'm Mino Elsa.
And I'm Grant Race.
So this is Lamora, our senior design project. So we are also, to be into a third time, entering into the IT Studies Global Innovation Awards Design Competition. Again, the kind of goal of this is to develop a houseware product to solve an issue, demonstrate the research you did behind it, the process and storytelling behind the design. The difference for us is typically this project is entered by, either a mix of engineers and design students. Although we are a team purely of just us three engineering students. So there's no design students on our team,
Industrial.
industrial design students. So what was our problem? So conventional cutting boards used in household kitchens accumulate harmful bacteria and are difficult to sanitize between uses, creating a food safety concern. This requires a hygienic self-cleaning solution that sanitizes a conventional household cutting board, regardless of cutting board material.
Introducing Lamora, a high-end device that's intended to sit on any large kitchen countertop space and clean a multitude of cutting board material surfaces. This design is simple, sleek, yet exudes luxury.
So what is it like to use? It's quite simple. All you do is simply rinse your board to get most of the large material off. So it looks clean. And then place the device place your cutting board into the device. It'll then dry and sanitize it. Outside of that, there is a start cycle button, a power button, as well as 3 lights. A red light for an error, a yellow light for in cycle, and a green light for the cycle complete.
So when conducting some background research into patents on UV being used to clean items, we found on the left here a patent that really revolved more so around cleaning kitchen utensils. It had everything to do with different compartment sizes for different utensil sizes. And then on the right here, we have an expired patent that more so dealt with just the overall UV chamber. But the purpose of this is that it's multi-purpose. So on the right there, you see a little tea kettle. And really, we didn't find either of these too useful in what we were trying to do. When looking into the market space, there's really only one competitor, which is seen on the bottom there. And all these variations include thin plastic cutting boards, and you're also provided with knives. So this introduces an issue of what if you don't need more cutting boards? What if you don't need these knives? What if you don't want to use them? So our device is meant that you can use your own cutting board. And it also is aiming to have a faster cycle time than our competitor.
So going into that a little more in depth. So with hand washing, you can use any material board, but doesn't UV sanitize it for you, doesn't dry it for you, and also doesn't save you any time. Axiom, which is the only real competitor in the space, again, comes with 4 cheap kind of plastic boards. And if you don't like plastic, well, that sucks, because all you can use is plastic in it. But it does supposedly UV sanitize. It does not have any drying capabilities. And it also comes in at around $120. But it does save you a little time. Versus Lamora, where you can use any board material, it'll UV sanitize, it'll dry, will be a bit more expensive, but will save you significantly more time.
So when looking at this device, we really saw three clear subsystems, two of which fell into function, which have more to deal with how the device cycle runs and how it will operate, and the other one falling into form, which deals with user appeal and how the device will look on the exterior. So our first functional subsystem, which was led by me, was our UV thermal and convection aspects. And this was focused on the primary sanitizing and drying functions of our device. This had anything to do with the calculations and the cycle times of those topics. The other functional subsystem was the controls, user interface, and power management. This was led by Joey. And this had everything to do with our electronics, software, user interaction, things such as the implementation of the power, your control circuitry, and your user interface. And then our third subsystem, which fell into the form category, was led by Mino. And this had everything to do with the ergonomics and exterior housing of the device. So this was how the exterior of the device would look, how it should feel, how the user appeal, how they interact with it, so on. Back to when we were conducting our research, we found some key codes and standards. The first one being given to us by the US FDA. So to avoid our device being classified as a medical device, which would obviously come with rigorous approval processes and cost, we have to market it for general households and make no medical claims. The other one comes from the Federal Insecticide, Fungicide, and Rodenticide Act, which is that any device that claims to kill or mitigate germs is considered a pesticide device. So to legally make these health claims, we'd have to have EPA registration and conduct some laboratory testing to prove that it works.
Along with that, there's also some electrical code standards that you have to follow. All of those center around preventing shock risk, overheating, fire. So what that means is to legally sell a device for household use, the electrical systems must include proper grounding, insulation, overcurrent protection, and voltage regulation.
Moving into our functional objectives and constraints, which once again revolve around how the design operates and runs. Our first objective is that it should complete a full sanitize and dry cycle in under 45 minutes, so that we're faster than our competitors. The UVC subsystem should maintain output for a lifetime exceeding 8,000 hours, and the user interface should provide immediate and recognizable feedback. Our constraints are that the design shall incorporate safety interlocks to protect the user from harmful radiation. The UVC subsystem shall deliver 1.67 millijoules per centimeter squared across the entire board surface. And this was proven by a study done in a scholarly article as the benchmark for achieving 99.9% reduction of common foodborne pathogens. All internal components shall remain below 75 degrees Celsius, and the design shall operate using 120 volts AC power and draw less than 1 amp. So moving into our UV, down selection for our UV light components included first how the UV method would be. Some of our options included UVC LEDs, low pressure mercury lamps, low pressure amalgam lamps, pulsing on flash lamps, and excimer lamps. So really your main issue with mercury lamps and amalgam lamps is that you're introducing a toxic chemical into both the user and the food area. And then your flash lamps and excimer lamps are just more complicated, way more expensive, and overkill for what is required. So for those reasons, we ended with this seal module of UVC LEDs. Moving on from that, we had how would you apply the UV light? So you can either do a stationary array, moving scanner, much like a copier, moving the object under the light, or a robotic arm that would be programmed to move to specific spots. And we decided to go with stationary as it includes the least moving parts, making it less complicated and less that could go wrong, as well as guaranteeing a uniform light distribution. We also had our thermal and convection down selection. So for those options, we decided to go with a PTC heater and fan. We found that this was best as infrared drying lamps would take up a lot of space, and microwave heating is not really an option when dealing with metal components, and a heat pump and dehumidifier is just not required for what we are trying to do. We also decided to go with the forced convection fan to move the heat through the unit. And when looking at how the heat would leave, we decided on going with passive ventilation, which we will touch on later after experimentation.
So then we looked into power and placement of the electronics down selection. The three main options that were looked at were battery powered, AC wall outlet, or a combination of the two. Originally, we kind of thought we'd do the combination of the two, but at the time of down selection, there was just inconclusive of what was really the important parts. So it required further testing to really determine what we would use. And then along with that, the same kind of thing goes for the placement of electronics. We had ideas of where we could place it, but again, until we really experimented with the design as well as actual experimental testing, it was inconclusive on what we should do. The sensing equipment needed, we really wanted two main measurements. We wanted temperature with inside of it, and we also wanted a measurement of the location of the door. And to do so, there's millions of options for temperature sensors, but we decided to go with this Fidgets ecosystem, which is a family of products that integrate with each other very simply, very easily. So we went with their precision temperature sensor. It will read you -50 to 150 degrees C, plenty of range for us, and it doesn't need to be extremely accurate. We've seen a general air temperature. And then kind of going along with that, there's lots of options for switches, whether it's mechanical, infrared, magnetic. We ended up going with these magnetic contact switches that Fidget also offers, with the dual benefit of getting us our measurement door, whether it's open or not, and also helping to hold the door closed.
Now moving into more of our form side of things, we have our design inspiration. This design was greatly inspired by computer housings as a whole, which is the left and the right here, for their clean, modern lines. This is the one on the left for the curves, and also just some technologically advanced things, as well as this one on the right here, implementing form and function with these exhausts on the side. And then for the namesake and also some other elements, we took some inspiration from the moon, hence the name Gamora, as for that light, smooth, subtle feel. For the down selection for form, the first thing was, as Joey mentioned, was the orientation of how we're actually going to set up this product. As you saw, the competitor was a vertical orientation where you put the cutting boards in on the top. The other option is a horizontal orientation. We ended up going with the horizontal orientation mostly for stability factors, being that this is a device for a generic cutting board. It can be large or small, and if it's vertical, it's going to have to be a very large vertical device and lose some functionality with that. On top of that was the vent location. For this, we considered all the sides. It came down to either on the top or on the side. Eventually, we did go with on the side, being that on the front face. Next was the water collection, being that you have to rinse this board, put it in the device, and then there's a fan, and then it dries and all that. There will be some water in the system that we have to expel. And two options for that was a removable drip tray or a passive drip tray. Eventually, we did end up picking the removable drip tray for its cohesion with the device. And lastly is the housing material. It's important to note this was very early on in the process and more so prototyped housing material focused, which is why we ended up with ABS instead of some of the other options. But going forward, for the actual product, it would be a combination of ASA, stainless steel, and aluminum. Moving on to the form objective and constraints. Some of the objectives included the design should be able to use multiple times before any cleaning or charging is necessary. The design should not weigh more than 10 pounds, and the design should not cost more than $300. On the constraint side of things, the overall product size must be less than 15 inches by 6 inches by 25 inches. This was taken as kind of the generic size of the kitchen from our experiences. The design should support, or it must support 10 pounds on the top of it, as well as the device has to be able to accommodate a 1.5-inch thick cutting board by 12 inches by 18 inches. So these are the first sketches, and I'm not a Maya student, so they're going to be a little bit more rough than what we saw earlier. This being the first sketch of just what it should look like. It was very rectangular, boxy. The whole construction outside was made of sheet metal. This first iteration put the vents on the top. And then this is that second iteration built off of that idea. We have our heating fan in the back. This one was a passive water collection system out the back, as well as a pull-out tray on a wire mesh, so you could put the cutting board on and then slide it in.
And this was still a battery operated version. This is built off those last slides, so these were not drawn to any sort of scale, just to visualize and see how many or where our components can fit based off of where the UV lights need to sit and where the components need to be in relation to each other. And at this time, we're still debating between battery or outlet power. And then after those, we decided that the design was a little too rectangular and didn't have enough form aspects to it. So we decided to come up with some functional fins to help exhaust some of the heat, but also for appearance sake. And we went with the option B here in the middle, which is a perpendicular to that vertical wall, and it has that crescent shape, again, complementing the moon inspiration. Which brings me to the first CAD model. Some of the notable changes from the sketches is this ergonomic rod. It used to be a knob, but then that wasn't seen as a good enough way for a person to hold a cutting board, open it. Makes more sense to be a rod. This outside material was aluminum sheet metal, still, like I mentioned, battery operated. We have a drain plate here to push all water into these side water trays, which you can remove yourself and empty out. And they've been oversized for the amount of water expected to drop off the cutting board to make sure to fall in with those objectives and constraints that you can use this product multiple times.
In parallel with that, Grant and I were also doing some experimental testing. The goals of our testings were two main things, and that was how long does it take us to dry a board, and how much power does it draw while it's drying that board. So we started with 7.5 grams of water or 2.5 grams of water on the board, and we would measure the weight of the board every 2 minutes for 30 minutes. With this testing, we also tested it with and without a slant on the board, and with or without an active exhaust fan in our setup. So if you see there, the cutting board is just kind of on the bottom of the lid of our tub, which happens to be almost identical to the size constraints of the product. It also uses the heater that we plan on using for the product.
So taking a look at our experimental data from those experiments, we measured water weight as a function of time. So as Joey said, we had our 7.5 grams case, which is really your worst case scenario. A user would quite literally have to take a cutting board from directly under the sink, spilling no water, all the way over to our device, and not shake it off, not dry it or anything. Whereas your 2.5 grams water case is much more your typical rinse and shake off. So when we're looking at the left here at our nose slant, you have really, you can see that there's no difference between including an exhaust fan or having passive ventilation. And then when you take a look at the right data, which included a slant of 5 degrees as depicted at the top, this is towards our fan heater. So what we saw was much more significant water weight decrease. And once again, an exhaust fan was just deemed not necessary. So after conducting this testing, we decided to go with the passive ventilation, and we decided to include this 5-degree slant.
At the same time, with the power consumption requirements, we also determined that battery powered was not a good solution. So this is the point where we pivoted to a AC wall strictly powered product.
So now that we have determined our drying cycle time of 30 minutes, we're looking at our UV cycle time. So some of the main calculations we're looking at here is given a 120-degree view angle, you have your two different distances. One, when you have a really thin cutting board, so you have a further distance away from the lights, and one when you have a thicker cutting board, so the light is closer. So what we're looking at here then is our effective light bandwidth, which at the worst case scenario gives us 5 inches in diameter. So when we're looking to cover a 12-inch by 18-inch cutting board, that means we need to configure the lights in a 3x4 setup so that we can guarantee that we're hitting every point on the cutting board surface. And then the main calculation that came from this is located on the bottom right. Given when our lights are the furthest away from the cutting board, the cycle would require just over 100 seconds to complete that UV dosage requirement. So that is what our cycle time would look for the UV.
Which brings us to our current version of the product. So this part of the design came with this, material specifications for each component. as well as what Joey mentioned. It is now outlet powered, so this is power cord to the back. So the material for the outside wrap is now steel, stainless steel, because I did some stress and deformation testing in ANSYS and found that with a 20-pound load on top, because I wanted a little bit of factor of safety in there from our 10-pound constraint, that the design would crumble with the aluminum sheet metal. So we added stainless steel instead for the outside wrap and this ASA internal support structure to support that steel under the loads. The ASA internal support structure is a combination of the drain plate from the previous design as well as a support structure to support this design. And then that front hatch is going to be aluminum, and both the steel and aluminums are PVD coated. Oh, and lastly, this version had a integrated CNC fan cover. The previous version, which didn't see in the image, was a fan screwed into the back. This is much more sleek, modern, user-friendly.
So then going into our simple electrical diagram, basics of it is you take your 120 volt AC, it's transformed to 12 volt DC, and then there's two main subsystems that are controlled by solid state relays with the microcontroller. One is the heater and fan, so you run the heater and fan cycle, and then that shuts off, and the UV array then turns on for its cycle. And then once that's complete, the cycle's
Which this here is the exploded view. As you can see, this is how the parts kind of work together, condense all into this main housing. Here's the parts listed for the exploded view. There's still some parts to come for next semester, but yeah. Which brings us to more in the real world. These were all created thanks to Gemini Pro. Big shout out to that. And so the left and the right here are how the product would actually be used. So normally sitting there or in use would be on the left, and then the user actually loading it up, taking the cutting board in or out. And then down here on the right is more of a jab to our competitors, because if you look them up to buy it, it doesn't specify anything about UV light, just purple sanitizing lights. So obviously we never see this in use with the purple light and the hatch open.
So what are our plans for next semester? So there's still some refinements and design improvements to be done on our final version. And along with that, the large goal for the next semester would be creating a working prototype with UV lights and all the controls. And then lastly, we'd like to create kind of a prototype packaging setup. So you can, at the end of the day, you can see this whole product and prototype, what it would look like on a shelf. Any questions?
All right, thank you. Okay, questions, me first.
Okay. So I want to kind of go back to your, not just the problem statement, but also some of your objectives. I didn't see anything in like how you would clean the system. So, you're envisioning this is going to sit on somebody's counter in their kitchen where you will have moisture and grease. Was that something you talked about or you considered?
Are you describing the cleaning of the interior? Or
No, how to make sure that this thing doesn't look gunky after 2 years of use.
Yeah, so I mean, with a stainless steel exterior, it would look gunky.
Well, no, okay. Well, no, I'm just I'm saying that I think that might be something like if you could consider, you're gonna get grunky dust inside all of those things. I have it on my microwave fan and it annoys the bejeebies out of me because the only way to clean it is for me to get power tools out, disassemble the microwave and or put Post-its over it. So I mean, I think that when you're looking at a household product, you also need to kind of consider what's going to happen as it's used. So I would consider that. And then, did you look at all in did you expand your research to consider some of the UV cleaning products that are out there that may not be targeted to cutting boards?
Yeah, so they have other things that are kind of marketed as just like a cabinet, I guess, like just like almost a microwave, but it's just UV light. And then with that, the user would have to set the time for the cycle themselves.
Oh, no, just to get some ideas. That's more where I would, in your background research, because I know there are products that you can put your cell phone in. There's products that like are a wand that are marketed for disinfecting with that. So it was more like in terms of getting ideas for your project, you can look beyond that particular focus.
We did look at like the cabinets, the lawns.
Yeah, that's,
And the last question I have, and this is a little facetious. So your initial picture of that grunky cutting board would not be cleaned by your device. It would just be sanitized.
It would be Santa.
Yeah,
That's what we're, so
that's false marketing.
we did joke about this when we were making the presentations, but did find the most horrific looking cutting board I think I've ever seen for that picture. But the point that we should a little harped on a bit more is that, with a brand new cutting board, there's really not much place for vector to hide, but as you use it and you create those grooves, that's where the issue becomes. And I don't know about you guys, but I don't think I bought a cutting board in the last 5 years. I don't think my parents have bought a cutting board in the last 10 years. So they all.
That was just kind of, that was facetious. Nice project.
Okay, time, maybe one or two if you have any.
Yeah, I have one question regarding the cost you mentioned, that the cost shouldn't be more than 300. So is it just the cost of the product itself? Does it include maintenance or cleaning, for example?
It's just the cost of the product.
Okay.
The hope was to be a product that would be, still elegant, so not super cheap, but not like absurd where it's very, very niche.
Still competitive with the competitors that are in the same area.
Okay, and the second question is for, let's say, your plan, how will you ensure that the device is safe, like from any radiation or toxic chemicals? What kind of analysis that you will do or testing after you develop your prototype?
Yeah, so I guess one thing that we don't really know is how you would test for that UV leakage, but I know for sure the point of the interlocks, those magnetic switches, they're on the door. And so that red error light that I talked about is if that door opens at all, it immediately cuts the power to the UV lights and to the heat. So it just shuts it down basically if the door's open inside.
Sorry, you have one more?
No, I'm fine, thank you.
I was gonna say, we maybe have time for one from general audience. Go ahead, TJ.
What made you want to have your hatch open up instead of down? I saw that, you had your control panel popped out a little bit and I'd be worried, open it and accidentally clip it something.
So the panel is actually fixed. The door opens, the panel stays there. The panel's on the actual body. The door just kind of goes in around it.
Well, yeah, I was just like, why would you want it that way instead of opening it down where you wouldn't have to worry about going over the control panel at all?
Yeah, so this is a topic of debate for us. We chose to go with up and then we kind of stuck with it. And that's one of the things with that, there's some design things that we want to change, look into is definitely that door opening arrangement.
Yeah,
But you got the route on the front too, and you open down, you've got some angle, that's the door that you can't pass.
what I was gonna get into. So if we're talking about the 1.5 inch thick worst case scenario cutting board and you open it downwards, you have that angle. And then since the slot for the cutting board kind of has to be on the downward side, otherwise all the electronics have to sit below where the water is going to go, which makes a lot of extra layers there. You're forcing the cutting board to sit on the bottom and then go over that angle with a relatively large thick cutting board.
Okay, we gotta move on. Thank you, guys.
Yeah.
Thank you.
Thank you.
Appreciate it.
Sure.
I gotta get out of here. So thank you. Good job.
Fingers on the competition. Yeah, all right, there's a competition. I don't know.
Oh, yeah.
I think they're according to the other advantage of kind of like the my side, right? Give them an interesting brand and music.
Yeah.
It's
So while we're setting up.
Morning.
Yeah, I'm here. Let's line up. Yeah. Panic crew. I double check the schedule.
You made it.
Funny, it wasn't funny, but just for a moment, I thought it's supposed to be 11 and finish it.
Okay, I need another sheet.
Oh, well, he's not, but
Right.
Well, you can, I'll move in.
You're on-
like if we talk like both sides, we're good, right?
Yeah,
Okay.
we now like have, yeah, that, actually, yeah.
A little better.
Should we put like a mark on the,
I was thinking about doing
Sounds
that
like a
actually.
good idea.
That's-
It's almost this line because you
Yeah.
can't see this line.
But the,
I see the bottom corner of that video. No, I see the bottom corner of the,
Yeah.
this.
Yeah.
See that? So I mean,
Yeah,
you're perfect.
you're in, you're in.
Alright, that one. Well, please, well, we'll switch.
I used to do that in
I don't want to be in.
Yeah.
2020.
Yeah, with COVID, yeah.
You're out of frame, but you're barely in.
Jeez.
You should move forward so we can see your face.
Are you expecting the Hollywood agents to be watching this? Is that right?
Apparently.
Actually,
We're practicing for August.
there you go.
Okay, so 12 o'clock, I'll go ahead and get started with the last talk of the session on, lunar environmental testing chamber, so take it away, guys.
Sweet. Alright, so I'm Ethan Hazelwood.
I mean, Rasmussen.
Mitchell Rust. And I'm Clayton Flores. And we are creating a lunar environmental testing chamber. So kind of getting into a problem statement and like a little bit of background of our project in general. So kind of what is the Lunavotics competition that we're designing this for? So it invites top universities from across the country to design and create a lunar rover with the main goal of excavating. So these rovers, they pick up regolith, they cross an obstacle, and they deposit into a single berm. This is last year's rover at the Artemis and actually at the Reno respectively, and his name is Davey. So getting into our problem statement.
I think you're holding it upside down. There you go.
There.
All right.
There you go.
So what currently exists to the team itself? So the team does two types of tests. They do subsystem testing as well as a full-scale system testing. All subsystem testing has to be created independently. So each test requires its own test fixture as well as its own testing place. I've seen that's a driving test for different types of wheels and sand pit. And the only full system testing available to the team is taking the entire rover to McKinley Beach in the spring. Wisconsin has really great weather in the spring, it's completely reliable. So as well as getting a van and getting the whole team to go out. So it's always a fun task. So what our group is looking to create, we're looking to create a testing chamber that replicates the competition environments. This mainly focuses on the driving and digging aspects. We want to enable full-scale system testing, not make it a hassle to get the vans, go to the beach, make sure the weather's good. We want it to be compatible with testing fixtures, so we want to be able to still do subsystem testing all within inside this chamber. And we want it to be safe enough to exist in a lab space where the rest of the Lunavotics team will work around, but they don't necessarily have to be wearing PPE or have to worry about the actual regolith itself.
So we don't have quite enough time to go through all of the extensive research we've gone through. This being a research project, there's been a decent amount of our time has been looking into different topics surrounding the project. But we're just going to start with what is regolith. So this is a microscope sample of actual lunar material collected during the Apollo mission. Some really interesting properties is its geometry and size distributions. Some things you can't see here are also reflectivity as well as electrostatic cohesion. There are some elements of this that aren't replicated in simulant, as you'll see in the next couple slides, such as these kind of crazy microstructures with like porosity and some strange like jaggedness. That's due to meteorite impacts on the moon. That's hard to replicate here on Earth. Earth soils are often more like this, which are some common sand samples. You'll see that they're very round, very normal in shape and size. And the geometry and mechanical differences between these two types of materials account for a lot more than just density changes. So when we're doing digging and drive testing, we notice a very big discrepancy between what we find in testing and what we find in competition. So a lot of our iteration comes on about a year scale. We can't go like that, say teams out to the parking lot and drive it around. We could, but we're not testing in concrete, we're testing on an actual lunar simulant. So these are the samples that we see during competition under a microscope provided by Professor Schaefer. This is lunar highland simulant, which basically takes the role of the materials found on high points of the moon, like mountains and hilly regions, what they call the highlands. And this is what's called black point 1. That's what you'd find at the bottom of like a crater. They're similar in mechanics. We do see some discrepancies between competitions because this is what's used in the preliminary runs at the University of Central Florida. And then NASA themselves used these at our finals competition. They have the same luminosity properties that you find in an actual simulant, as well as a lot of the jaggedness and differential in size and shape that you'd expect to see in it as well. So this replicates a lot of the important mechanical elements of simulant, well, or as proper lunar regolith, without worrying about chemical composition, some of those other factors that we're not necessarily worried about. When you go a little closer on the scale, this is what you kind of see. It's kind of blurry just because it being reflective, you have to be really careful with how you light the subject. And if you compare this to actual lunar samples, you'll see that they are fairly similar. It still is missing some of the, obviously these are not scaled quite the same, but you'll see it's missing some of those crazier elements of geometry, but it still is jagged, sharp, and it distributes size very widely. So for us, this means that traction is a big issue. A majority of the teams that actually make it to competition don't end up driving at all. They end up spinning their wheels in place and just digging themselves in the starting area. And that's a very big problem. Our team actually does very well in drive, but again, it comes in an iteration cycle of about a year because we can test on the beach and we're totally fine. But when we go to competition, even last year, we saw our wheels were spinning wildly in the wrong direction while driving to do our steering, not being strong enough to hold in place. That also makes weird excavation modes. So right now what we do is we dig in sand and we compare densities to try to extrapolate what we expect the loads to be. But this is not perfectly accurate. NASA doesn't recommend this by any regards. The material itself actually collects in an entirely different way, and you don't get the same volume in your digging source as you would when actually using lunar simulant. Dust management is a big problem in space. There's common stories about spacesuits being gummed up basically immediately upon landing on the moon. And that same thing goes to us. It sticks to everything and it's sharp like glass. So that makes it very difficult to manage. Right now, our basic idea is just to provide redundancy on all electrical enclosures, boxes, and mechanical systems. Visibility is also a problem. As hard as it is to get a microscope picture of it, it's also hard for our cameras to see it while we're trying to path. This is an autonomous mining competition. So trying to do it through computer vision is very difficult when everything is gray and everything is a mirror. For health hazards, I'm just brushing really quickly through it. The most common hazards that regolith is it's irritating to the skin, eyes, and respiratory system. So that basically means that when you're in a testing environment, you have to PPE up. That includes gloves, a dust suit, booties on your shoes, masks, and then goggles. And then the judges themselves also use a 3M provided full respiratory system that has active filtration. So these are something that you'd have to have in when you're in the chamber, when you're actually working on it, and you'd have to have that kind of safety list posted on the system itself. But obviously, you don't want to always be wearing it when you're in the lab. So we also have to make sure that the air is filtered coming in and out of the chamber. And we're going to do that via a negative air pressure system. Right now, the standard we're working with is the same one used in clean rooms and hospitals, which is kind of a different scale because they're worried about bacteria escaping. That's slightly smaller than what we're working with, but we're still working with very fairly small particles. And you can accomplish this with basic HEPA filters. So we're filtering all the air in and out, but we don't want to replace it very often. So NASA also recommends we look into mechanical filtration. So these particle separators will also be on all exits of the facility.
Awesome. Well, I'm going to take over the constraints and criteria portion of the presentation. So our first aspect was we want to be able to fit the full rover. We want to have full scale testing. That's something the team lacks right now unless they go all the way out to the beach. And when your first full scale test is at competition, if something goes wrong, that's a pretty poor time for something to go wrong. Next, our chamber footprint. The allotted space we have is about 4.5 meters by 4.5 meters. We aren't going to take up that entire space, but we thought there's like a minimal area we wanted to do 3/4 of a meter by 3/4 of a meter. We want safety and we want safe access for people. So when you're going in there, Mitch talked about it, like the PPE, the standard procedure, knowing the threats that regolith has. And we also want it to be safe for like unsuspecting bystanders. We don't want somebody to walk in there and get like affected by regolith. We want it to be able to fit through a standard doorway, and this is the sense that it can be taken apart and can be moved. We anticipate at some point in its lifespan, it's going to be moved. We want it to be useful for years to come. We don't just want it to be, we make it, fill it with a bunch of regolith, and then it gets thrown in the dumpster when they're building a new building. So we want it to be able to be moved somewhat easily. We want it to contain an acceptable amount of regolith particles, this being, we want to replicate those competition conditions, and we also don't want particles being flung all about the room. That kind of goes with the safety. We want repeatability in our testing. This is a big one. Have a starting point that the chamber can be reset to every time and that it can be accurate, and how that accuracy of competition conditions is going to provide the Lunobotics team a major advantage in competition. We want it to be structurally sound. This one's pretty self-explanatory. You don't want a 2x4 hitting your head, or you don't want it collapsing on you or falling in a regolith pit or having it spill out everywhere. So we want to make a good structure. We want it to be safe and functional. This safety, we've harped on it a lot. We want to make sure this is safe. And then functionality, we want to make sure that it actually helps the team and gives the team an advantage towards that competition. And then we want it to be manufacturable. We want us 5 individuals to actually be able to make this thing. And then we want to stay within our budget. Our budget is our big constraints, and we're working around that and really like spending any dollar we can get and finding extra dollars in anywhere we can get. So yeah.
Coming off those constraints and criteria, I'll run you through our decision making process. So first of all, we wanted to create a standard pit design that would be featured in every chamber. So the reason for doing so is just to have some consistency throughout. We really wanted to address like differing ideas of how to enclose the individual regolith chamber itself. So the most important weighted criteria for the regolith chamber, or the pit rather, is going to be whether or not it's reasonable to attain within our senior design project. We need it to be reproducible, and we also want it to include enough space for flexibility of testing. So some of the biggest things that we've talked about previously is like being able to have full scale testing. We want the rover to be able to produce as many movements as it would naturally in the competition environment, because that currently doesn't exist. Moving on, we have a slide here just kind of designated for the regolith pricing. When we were preliminary looking through the pricing for regolith earlier on in the year, it was a lot more affordable and actually seemed attainable, and we would have been able to fill our entire regolith pit. However, due to your current administration and tariffs, we're seeing a dramatic 2.5 times increase in pricing from regolith on all sources, which is going to lead us to fill it about a quarter of the way, or what would equate to about 18 inches in size. So
Just give me a size here quick, before we move on. Just give me a size quick. What is the dimension of that thing quickly?
3 meters.
Right.
we ended up choosing the largest possible attainable pit because it would give us the most full system flexibility of testing. So initially every team member created one design, and then we narrowed them down from a list of 3. We have the open pit, which wouldn't contain the regolith pit itself. It would just be regolith in a free, huge pile. We have the vestibule, which would contain a small walkway before the regolith pit, so it would allow people to enter the pit without having to be fully PPE'd up. And then the crane option, which kind of focused on trying to incorporate different machinery to load the actual rover inside of the chamber. The 3 heavily weighting criteria for our decision matrices for the actual chamber enclosure was the cost flexibility, the dust mitigation, and the ease of testing. The open pit scored pretty high on cost flexibility, but it doesn't mitigate the dust as well, and it's not quite as flexible. The crane would have made it a lot easier to actually run tests, but you would have to dish out a little bit of extra money to support it and buy the crane itself. So ultimately that led us to choose the vestibule design. I'll hand it off to Ruth and she'll give you a walkthrough of our actual CAD model.
This is our preliminary model, including all the features that we want to include. So on the inlet here, we have a HEPA filter. So the air comes in towards the front and then exits in the back. So it is near the door. So when you open the door, the air flows into the chamber instead of out. So no particles are able to go through the front door. And then we have a magnetic door here that seals. And then behind it, there's an accordion door. So this door is lockable, so people that don't know the proper safety standards can't use it. And then It opens up to 51 inches wide. Our rover is 28 inches wide, so that allows plenty of room for people to carry it into the chamber. Then here we have a shot back and particle separator. So we're able to set the rover down on the floor in front of the pit and clean it off. At competition, we often see the regolith clings to the rover, so we want to be able to clean it off before we take it out of the chamber. We also have a particle separator to separate the regolith. And then we have PVC piping here. So the shot back plugs into the PVC piping, and then after a test, we can turn it on. It's got 44 minutes of continuous runtime, and then it'll pull the air out of the bin area and then separate the dust out. And then we've got a pegboard over here where we can have different mounting. We can mount different testing components, so we could run system level or component level testing, such as the wheel. And then here we have the exhaust part of the air filtration. So we have a cyclone filter. So the air comes in from the side, goes through a spiral, the dust falls off the bottom through gravity, and the air is allowed to escape up the top. And then from there, it goes through a HEPA filter, and then an exhaust fan takes it out. It has 346 cubic feet per minute. So it is able to turn out the air 12 times an hour, which is the same standard that hospital programs use. And then for the siding, we've got a clear vinyl on one side for viewing for team members to watch the testing. This is used in porch enclosures and barriers, so it is a rugged outdoor material. And then to save costs, the rest of it is just transparent greenhouse sheeting. Then we've got an electronics compartment and data port. So we are able to monitor the pressure, temperature, and humidity, and the pressure in and out of the chamber. So then we can control the fan to increase speed as needed to keep that difference in pressure between the chamber and the ambient. And then we can also monitor the temperature and humidity while we're doing testing, so we can report that. And we also want to make sure that we're keeping the humidity at a low enough value, because if there's too much moisture in the regolith, it can start to crystallize. So we have desiccant packets that we can just microwave once they're saturated, and then replace, put them back in the chamber. And then we also plan on having data ports, so cables can be run in and out of the chamber during testing. And then there's also a winch and pulley system here that allows us to do more testing. We can do drive-by testing. We could simulate microgravity, and we can also assisted lift the rover into the chamber. And then we also have a garden weasel for resetting the pit, so we can have the different, we can reset it each time we do a test. And then we've also got chamfered walls in the pit. So if it was just to be in the box, it would be 362 feet cubed. We can half that by putting the chamfered walls, and then we just need less regolith to fill it up, saving money there. And we do want 3 feet deep because the regolith acts differently when it's near a wall, so we want to make sure that we're producing the same that it would see as if it were on the moon or at competition at NASA. So once it's in the middle, then it's got that full 3 feet on each side and can do its main testing there.
All right, so I'm going to give a quick rundown on just our budget and our timeline. While it's a little preliminary, we'll go over it regardless. So the funding that we've received, we've got the $1,000 from the Senior Design Fund. It's awesome that we were awarded the Wisconsin Space Grant, so we have an additional $5,000 there. The Milwaukee Tool sponsorship, we have an asterisk there because the funds have apparently been allocated, but we do not know when we are going to get our shop vac or what tools we are going to get. So they're allocated. I'm told we're pretty much guaranteed to get it, but that's what comes into our cost of having like the flexibility, this buffer right here. So we do have a little bit of a buffer cost, but with our total funding, I mean, we're planning on spending every penny we get. Budget was a big constraint, and any dollar we get, we're going to make use of. So then I'll get into our timeline. So right now we're here, we're having our formal design presentation. We've been continuing our design evaluation. We're gonna continue that into the second semester. Our final design, we're gonna finalize that, starting the second semester and continuing over it. And during that, we're gonna start our build phase. Our build phase is, we're allocating a lot of time towards that because it's quite an undertaking what we're doing. We're gonna have our validation test, we're gonna have our design showcase, and then a cool thing, because we are taking the Wisconsin Space Grant money, we get to go to an event in August where we have to present what we use their money for. So that wraps that up.
Mostly regular.
Yeah, so thank you for listening, and is there any questions for us?
All right, go. Okay, Q&A, committee first.
Oh, no, you're on the committee.
I am on the committee.
No, I'm alternating.
Okay, all right.
To left.
First question, I have a lot of questions. Where do you buy the regular, by the way?
There's
Many places that distribute it.
there's research manufacturing companies. The actual place we test it actually produces the regulators.
Got it. My question is a lot about electrostatics, right? So there's these like notorious pictures of people on the moon, like coming off of their spacesuit into the regular all over the place because of the electrostatics. So have you considered that? Do you have like ionization guns that you're planning to use? Like how does NASA do it when you go to these test chambers? Like what's the story?
Yeah, so pretty much what they use at NASA at this test site that we go to, this is like their like public facing one. They basically just have shot back and just the entire thing. You're only doing about 15 to 30 minute runs at a time, so you're not necessarily living on the moon like you would. Electrostatics is a very popular way of removing dust because the reason it sticks to you is because it's electrostatically charged. If you introduce another electrostatic charge, it then becomes neutral and it no longer sticks. The team has researched pretty heavily on ways of implementing this into a chamber, but from what we've determined so far, it's out of scope of the project. It'd be really nice if certain surfaces within the chamber were electrostatically charged so that they wouldn't stick, especially just for cleaning, or have a gun, like you said, like an electron wand. But no, we don't have any plans of implementing it.
Okay. Yeah, I just worry a lot. It just could be wild really quick. You start spinning your wheels, all of a sudden it's blackout.
So that's kind of what led us to develop the idea of using that PVC piping system.
Yeah.
We're not certain yet if that's going to be 100% effective.
Well, you can see this is the Artemis Arena at Kennedy. They use a very similar system.
Yeah.
Okay. So they basically just pump air through it, and then it just sucks the air out of the air, or out of the regolith out of the air, and it collects it in a particle separator.
Okay, got it. Another question is about just the structure as a whole. You know, you've got this shed kind of thing going on. You know, the 2x4s at the bottom or 2x6s, whatever they are. Do you have any plans to like seal on the bottom there between like the 2x4 and the floor? Like I think you guys have some space at the Kruger Hall, right?
Yeah.
Where you're gonna basically put this, and I know the garage floor there is not exactly perfectly like epoxied, right? Let's say. So thoughts about that? Do you really need it if you have negative pressure? Like how do you feel?
We haven't really talked about it a lot. We're talking about using liner sealing, but that's definitely something we can look at.
Better have some spray.
Yeah, that's not correct. We mentioned about like spray foam too.
But another one of your objectives and constraints is you want it to be mobile and portable.
Right.
And I mean, you're talking about putting 2x4s together, with nails, like.
Yeah.
Well,
Real
the entire
mobile is
idea is that the structure in and of itself will be modular, so every individual piece should be able to fit through a common doorway, and then we're gonna use tie plates to affix all of those pieces together, so it'd be kind of like assembling somewhat like an IKEA furniture.
Okay.
That's the whole. Yeah, we leave plenty of space, and with the negative pressure, since we're kind of going overboard on, we don't quite need, the same standards that a clean room would. But we know there's probably gonna be holes that pop up. We know there's probably going to be cracks within the floor and the walls. Realistically, it should account for any issues with that. The main goal is that when you open the front door, you feel that wave of air go in and not out. So as long as that's there, we're pretty positive that it's not just gonna passively flow into the circuit.
Do you have like this open door, walk in, closed door, open door, walk in, kind of like procedure for?
Yeah.
Okay.
Yeah, we looked into that. NASA has a very heavy standard that they use in their Lunar Gateway program they're currently running or trying to run. There's talks about having like a whole like vestibule area with like a door here, door there, on and off there, but it's got very large really quickly. So right now we've settled on an area dedicated to being outside of the like direct regolith chamber bin, but still having space to clean stuff.
Last one, and then I'll pass it off. Do you have plans to have like PPE inside the vestibule to like change into before you go in? Like,
If
you have
we-
PPE?
Before you go in the chamber. So vestibule is just like, it's in the same area, you're just not standing in the regular.
So where do you take it off to clean it then before you walk out of the room?
Well, you just clean off the rover and then you go out of your PPE.
Yeah, the assumption is don't be like that much on your clothes. That's what we noticed in competition too, because we just walk around the entire arena just to find fully PPE'd up.
We're using the standards that NASA sets in their guidebook.
Okay, cool. Thank you.
Now, actually,
You got too many. You can't decide.
no, I'm kind of like, see, I had 3 things of household and I'm like, well, this wouldn't fit in the household. Is there, and this is not, right, so there are other teams in this, within a 90-minute radius of.
Yes.
Did, and I don't, did you consider kind of allowing others to use the chamber?
Yeah.
Okay,
Yeah,
that could help with cost.
Marquette's a competitor on the competition too. They're a senior design team, so it's a much smaller team than we're
Yeah.
here. There was talks at some point at the University of Illinois Chicago to build like a large, like multi-million-dollar facility like this. And they were gonna have multiple schools kind of invest in it, and it'd be like a group project. But those kind of fell through like around COVID. So
Oh, okay.
they no longer exist. Currently, the schools around us are UIC, Marquette, and then there's one in Michigan Tech.
Yeah, well, maybe you could have Marquette come and bring a sack of regular.
Right, right. Yeah, we also want it to be part of like an outreach program because part of our team, we do a lot of outreach with the community, like Big Brother, Big Sisters stuff. And it'd be really cool if we could have like, RC cars or something, so they can see stuff actually work in their environment.
Yeah, if you get to that point, if you build a really nice structure and chamber and have test procedures, a big cost that's adjustable at the end is the amount of regulars you buy.
Right.
And if they want to use it, you could have them chip in at that point.
Yes. We've been looking at it, we're gonna fill it as much as we can, and then over the next couple of years, the team
Can
fund
do
more.
And you probably have to be regular the whole way, because I was thinking, could you like
That's
be
something that we have talked about and just kind of due to the nature of the way that regulator acts, they want to be able to simulate it as close that they do in the environment. Because I think you were looking into a little bit about like soil compaction mechanics and how that idea applies to regolith.
You could collect the bottom in sand, but at any height, basically at some point, it's essentially concrete at the bottom. So if you have like 3 feet of sand, essentially that's a concrete bottom. And then you go another like 2 feet.
You did kind of, like, you did kind of consider it. So
Yeah.
that's-
We consider like making our own as
Um,
well too.
I'm kind of like, so I think I have a 3-presentation thing for question. What was the most challenging aspect of the project so far?
Personally, from my perspective, I think the biggest concern is safety and making sure, like you highlighted it, like, is this going to be sealed to the floor? How are we going to ensure that this isn't going to become airborne? How can we verify that it's going to be isolated? So I think those are some of the kind of ongoing concerns, because it's a little bit difficult to kind of measure like how many ppm of regolith is acceptable in the air. I mean, the current standards for safety are based on like silica particles. So it has the same risk as silicosis or like cutting concrete or inhaling sand. But that's still like due to the particle size and nature, it isn't comparable to sand. So can we evaluate in the same ways or those types of things? That's what kind of sticks out to me.
I'd also like to add, we spent a majority of the semester working on research and then design morphology. So the morphology of this was actually really difficult. We had a lot of things we wanted to add. We wanted to recreate what NASA has. That's what we wanted. But there was the option of spending, millions of dollars on a concrete facility that would never be moved and school would clap their hands. Or, it's also the proof of it, one of the two. But there are a lot of things that we want to do subsystem testing, so we needed some sort of like modular attach point. We want to do full scale testing, but we didn't know if we had money because we only found like 2 weeks ago about the WSGC funding. So before then we had $1,000, now we have $6,000. It's a big difference. So we spent a lot of time in the like idea phasing and actually like fleshing out like what's all in this. We ended up with 3 main like designs. But before that, we had probably a dozen or so of like possible alternations of different things. This could look like a tool shed. This could look like, we kind of ended up like a greenhouse kind of thing, like a small greenhouse. But it could have looked like anything in a lot of space.
Very cool.
I have one comment that is just something for you to think about as you go forward. So you've kind of identified, you're not sure how the air handling with PVC pipe is exactly going to work. You're not sure how all the joints are going to seal to contain this, and you want this thing to be rigid. So think about between now and the time you actually build this whole thing, is there some like benchtop scale testing you can do to test those concepts, or is there some analysis you can do in between now and building this whole thing? That would help you.
Good idea.
Yeah, that's a great idea.
Yeah.
And that would definitely help.
Like toy micro machine inside there.
Yeah.
Let's spin its wheel too.
Well, just, put together some joints and evaluate
Right.
how stiff they are, the way you're gonna design this thing.
Right.
You can test out one corner.
I was also thinking about kind of making a small scale model of the chamber and evaluating it for its interaction with the regolith particles. So using all the same materials that we'd use and just see what that impact.
There might be
is
some like fluid flow analysis that's probably been done for chambers like this, with your inlet and outlet and flow rate, and like how many turnovers are you really gonna get? Like the volume works, but what is the path of that flow? Can you get your inlet and outlet in the right place?
Yeah.
So not like starting from scratch, but we could probably piggyback on something that's been.
Okay, it is 12:30, so we gotta break.
Okay.
Good job, guys.
All
All right.
these have been good.
That concludes
Interesting.
the session, so thank you very much for attending. See you at 1:30. Thank you.
Nice. Thank you.